Thanks everybody for showing up. My name is Sandy. I currently work at Remix, which is a company where we are literally doing all the stuff that I'm going to talk about. I'm going to talk to you about bus scheduling and combinatorial optimization with Python. I encourage you to raise your hand in the middle of the talk and interrupt me with any questions that you have. My head has been like buried in this world for a lot of time, so I probably forgot a lot of the context, and anytime I can help sort of bring it back up and clarify anything, so like the concepts sort of build on each other, that is great. Does this work? Go next. Okay. This is the Muni map in San Francisco. Raise your hand if you rode the bus in San Francisco. Cool, most of you. The company I work at, we build software that helps transit agencies figure out where to put these lines and then how often to run them. And so that was sort of our first product, and our second product was figuring out, we have this, so here's a set of lines, we know roughly how often they want to run. How do we get to actually operating service on the street and buses driving around? Ultimately, there's two things that need to happen for a bus to drive on the street. Number one, there's got to be a bus there to actually drive that trip. And number two, there's got to be a driver who can drive that bus and take it around. So we have this bus scheduling product that basically concerns itself with the question of how do you figure out which buses are going to drive the trips, and how do you figure out which driver is going to drive the trips, and what all the driver is going to do throughout the day. And today we're basically only going to be talking about the second half of that, which is the bus scheduling problem. Like, how do you organize drivers in a way that allows you to operate all the service that you want to operate? Who has seen a timetable before? Nice. Almost all of you. I was actually amazed to even find out that Muni has timetables. They run so frequently. You sort of just think of it as like they come every so often, but or in some cases that you just think of them not coming at all. But there actually is a schedule, a timetable that they intend to adhere to, and there is a bus that's supposed to be at Clay Street and Drum Street at 9:15 a.m. If you aren't familiar with what this looks like, basically we have the stops on the top, and each column is basically a bus stop. The bus is going to hit as it snakes through the city, and then each row is a trip. When we use the word trip, we mean the bus driving the entire route one time at a specific scheduled time. So this is different than a passenger trip of like a person getting on the bus at some stop and getting off the bus at some other stop. Every trip here needs to be driven by some bus driver. So the topic of this talk is basically how we've used Python to make efficient and smart decisions about how to split up these trips between the bus drivers, both within a single day and over the week. There's actually two related problems that we're going to consider separately here. So the first one is this one, aka we call it the Runcutting problem. And this is where we split up the trips within a day. It's called a Runcutting because each thing that a driver does is a single run. You're sort of chopping up the timetable or chopping up what the bus does to get a run cut. So one run is like this guy comes to work at what is like 9:15 a.m. He drives a few trips. Then maybe he takes a lunch break, drives some more trips. So the second problem is what we call the rostering problem. And the rostering problem is sort of a very similar problem. You're assigning things that happen to humans. But in this case, instead of packaging trips into runs, we're packaging daily runs into weeks of work for drivers. So we would say, okay, maybe this guy comes 5 days a week and drives this same sort of set of trips every day. Any questions about that? Or keep going? Sweet. So let's go back to run cutting. We've got a potential allocation of trips to drivers here. Each packet of trips is a run. There's two runs depicted here. So there's like magenta guy run. He's got this long break in the middle. There's cyan woman, and she's doing this stuff. Each run has some sort of cost associated with it, which is basically how much you need to pay a driver to carry out that run. For people who are coming in now, a run is a set of trips the same driver drives throughout the day. A trip is like a bus trip from some place to another place. Oh, sorry, what did you say? They're paying the woman less. Yeah, even in transit, there's wage discrimination. I don't know if that's true. So the cost basically depends on the hours worked, but it also might depend on like extra money paid for overtime or some sort of guaranteed minimum. We have these. Whoa, where do we go? We have these sort of, so drivers typically organize into unions, and the unions often set rules that limit the runs that are possible. So they might say a driver can't drive more than 6 hours in a row, or they can't have sort of like a split run where they get in early in the morning and leave late at night. So here is maybe another way to allocate these trips. Oh, go ahead. So this one you're saying. So yeah, this is probably me just visualizing it poorly. You would never have actually overlapping trips that overlap in time. Yeah. So sorry, that's a great point. This is a bad representation. A driver is only allowed to be in one physical place in time. Yeah, due to laws of physics. But so in reality, it might actually look like a little bit more interleaved here. So here's another potential allocation where cyan woman gets paid $130 to do all these trips, and magenta guy gets paid $120 to do all these trips, and the overall cost of the agency is less, and they like it better. So this gives us basically the run cutting problem. The objective is to minimize the sum cost of all runs. And this is dollar cost, but often agencies will throw in penalty terms to try to sort of discourage behavior that would make drivers have like horrible days. And then there's a set of constraints. So first of all, each trip has exactly one run. Second of all, there's sort of what's physically possible. So humans can't teleport. They can only sort of like drive trips that are in places where they are. They can't drive multiple trips at once. And then there's all these sort of labor rules that maybe it's not physically impossible to do this, but it's illegal, or not within the union contract. So this is a constrained optimization problem. There's some objective function that you're trying to minimize. There's a huge space of possible solutions. Each sort of possible allocation of trips to drivers is one point in that space. And then there's a set of constraints that sort of say a big chunk of this space is illegal for a variety of reasons. Any questions about that before we move on? Sweet. So the run cutting problem is part of this, or sort of can be modeled as this more general problem, which is a weighted set partitioning problem. And it's nice to think of it more generally because then maybe we can connect it to some other solutions or algorithms that have worked for these kinds of problems in the past. So thinking about it sort of from this lens, there's a big set of all the possible trips. Each subset has a particular weight. So if you take some set of trips, that's a subset, and the weight is just the cost of driving that run. And then you want to partition the big set into subsets, so you find a partition over that big set that minimizes the cost. Weighted set partitioning is known to be NPHard, which means it belongs to this class of computational problems for which there's no known polynomial time algorithm. Go ahead. The run cutting problem is NPHard, right? Because it is a weighted set partitioning problem, and weighted set partitioning problems are NPHard. So that adds sort of an extra difficulty to it, but so at this point you've basically figured out the routes. You've decided like where you want the buses to go. So the geospatial element sort of helps add in those like physically impossible constraints, because you can't have someone drive a trip and then immediately be on the other side of the city to drive another trip, but you're not actually like figuring out where the routes go as part of the problem. So for people who aren't familiar with polynomial time, basically it means that if you have like the size of the problem in, let's say there's n drivers or rather, sorry, n trips, there's no known algorithm that can that executes a number of instructions that's some polynomial function of n, which is basically a way of saying that there's this huge sort of space of possible ways that you could package these trips together. So if there's, let's say, 100 trips, maybe there's 100 factorial possible different combinations. I don't know exactly what the minimum bound on that is. So NPHard roughly means that nobody has come up with efficient algorithms that work for every instance of this all the time, but it doesn't mean that you can't get good answers some of the time. One of the standard techniques for these kinds of problems is known as integer programming. If you can express a problem in a certain way, there's well-known algorithms that will give you optimal results in often reasonable amounts of time. So this is, this diagram is just sort of visualizing the problem space. You can imagine, in reality, there's way more dimensions than just 2 to a typical run-cutting problem. But if you sort of like, imagine a simpler version of the problem in 2 dimensions, each point is a possible allocation of trips to drivers. You can see the objective function is pointing up. So basically, the higher you are in that graph, the better you're doing. And then you have these linear constraints. And so these are constraints that basically chop off or cut the graph in half. That sort of say this, like on one side of this line, there's legal things. On the other side, there's illegal things. And so you're basically trying to find the point that is the highest on this graph that fits within the legal constraints. The integer in the integer programming refers to the fact that you have these additional constraints that say you have to pick integer points. So you can see if you didn't have this integer constraint, maybe you could, let's see if I can do that. No, that little point on the left that says LP optimum would be the best because it's like the highest up and still fits within all the other constraints, but it's not an integer. You have some number that is that's not discrete, so that's not allowed. Any questions on that? It'll become a little bit more clear when we talk about the specifics of how we model this program. So luckily, there's a really nice Python library which allows you to sort of express your problem within this format. It's PuLP. I believe it wraps around coin OR. And so you can basically, with some really nice syntactic sugar, express your problem as an integer program, and then delegate it down to this really highly optimized C code to solve it in a semi-efficient way. So what does it look like to express your run-cutting problem as an integer program? Generally, the way you express the problem as an integer program is you define a set of variables. And your constraints are, you take some linear combination of variables and say, some coefficient times variable 1 plus some coefficient times variable 2 plus some coefficient times variable 3 equals some number or is less than or equal to some number or greater than or equal to some number. This will become concrete in a set. And then you define sort of a overall space that the variables can take. So in this case, we have a variable for each run. So there's this process that happens before where we just generate a bunch of possible runs. So possible sort of sets of trips that could go and be assigned to one driver together. So if we're looking back over here, magenta would be one run. So we could generate that magenta run. We could generate that cyan run. We could also generate this separate magenta run and this separate cyan run. And we're sort of just thinking of all the different ways you could throw a bunch of trips together into a single legal run that could be driven and satisfies all these crazy constraints. So you create a variable inside the integer program for each of these runs, and the variable is just 0 or 1. And the question is basically, are you going to include that run in the final run cut? 0 means that run is not going to be included, and 1 means that run is going to be included. So you've got a column here, basically, per run. The rows correspond to trips. And so these are just expressing sort of the very simple and straightforward constraints that you say each trip gets operated by exactly 1 run. So you don't have 2 drivers driving a trip. You don't have no drivers driving a trip. You have 1 driver driving each trip. So for example, if we look over at R2, R2 does not include the trip in the first row. It does include the trip in the second row. It does not include the trip in the third row, and it does include the trip in the fourth row. Any questions about this?
What does it mean that it's not a diagonal matrix? So let's just take the last line. R1 plus and R2 is equal to 1. What does that mean? It means somebody's going to drive R1 or R2?
So what this line sort of, what generates this line is we look at some particular trip and we see what are all the runs that include that trip? What are all the runs in this like large set of possible runs that include that trip? And this line is restricting and saying we can only include one of those runs. We have to include exactly one of those runs, because if we included more of them, we'd have multiple drivers driving that trip, and if we included none of those runs, then we'd have no drivers driving that trip. Does that help somewhat?
What you're saying is that when you looked at all the possible trips, that the only case there for somebody to do R1 and R2 was that they didn't do R3 or R4, and that in any case where anybody drove R2, they also had to drive R1?
So here what we're saying is basically we can't have both R1 and R2 in the problem. We have to have one of them, right? So if R1 and R2 were both 1, mutually exclusive, exactly. Right, and then in the line above that, we're saying that R3 and R4 are mutually exclusive. But we do have to include at least one of them, because otherwise we wouldn't be satisfying one of the trips. And so yeah, basically each column here corresponds to some run, and if we were to include it, there's a driver that would drive it. Oh, go ahead, yeah.
Check. I was going to ask, when you generate all the runs ahead of time, is that the set of all possible runs or just a random subset or what?
So it's a sort of, yeah, we try to generate the set of all possible runs, but at a certain point that gets a little bit big, and then we'll use sort of heuristics to pare that down. There are, all these constraints make it so that there aren't like a huge number of possible runs, right? Given what's physically like possible and what's legal by union labor laws, really sort of cuts down the set of like runs that you could have. But it can get pretty big. Any other questions? This is a piece that sort of took me a little bit to wrap my head around, so if I can talk about it in more detail with anyone after the talk. It's not like super essential for understanding the rest of the material. This one's not solvable? Okay, well. All right, well, hopefully this isn't our transit system, because then we'd have to change our timetables a little bit. So then that expresses the constraints. The objective function is fairly straightforward. Again, each run has some cost associated with it. It's basically just given the pay rules that the agency has, how much would they have to pay the driver to operate that shift. And so we're just minimizing this sort of like linear combination where we take the cost of each run, multiply it by that variable, which is going to be 0 or 1, and then sort of sum those all together. So then, again, we can use PuLP. We can throw it all in. This is what it actually looks like to do this. I think I may have actually just copied this from our code base. So you have a constraint for each trip, and so you're just going through all the trips. For each trip, you find here duty is the same as a run. A little bit confusing. But for each trip, you find the set of runs that cover that trip. You create this sort of like structure where you're just saying where you're basically gathering all the set of all the set of runs that correspond to that trip inside these variables that PuLP can understand, and then you add that constraint to the problem. RHS means right-hand side, so you're saying all these things added together have to equal that right-hand side, which is 1. And this is basically just putting together what we saw over here. For the objective function, again, you're basically just zipping up the set of runs with the costs for each run and adding that to the problem. So after that, you can basically hit like ip.solve, and it'll spit out some values. It'll spit out 0 or 1 for each run, and that'll basically tell you what your run cut looks like. So any questions on run cutting before we move to rostering? Go ahead. How long does it take? It really depends. So we've mostly been running on fairly small agencies, which will have something like 50 drivers. And in that case, it'll take between 2 and 10 minutes. When we try running it on much larger agencies, it'll take much longer. So this is actually giving the optimal solution. The caveat there is basically, or there's 2 caveats. Number 1, we don't always put all of the runs in there. So it's only giving the optimal solution with respect to all the runs that you've given it. And 2, the fact that it's NPHard doesn't mean you can never solve it efficiently. It just means you can't find something that'll always solve it efficiently. So there are going to be a set of problems where this would just spin forever and ever. But on most of the problems that we actually in real life throw in there, it seems to be relatively efficient. Generally, in the cases where it spins forever, it's because we've just like thrown a bigger problem at it. I don't think we've found a situation where it's like the same size problem and it like unexpectedly spins for a long time. Sometimes with their labor rules, it'll be impossible to find a feasible solution, and then they'll have to like loosen things a little bit or like change around their timetables a little bit. We did not explore other linear programming libraries as far as I know. So the nice thing about PuLP is I think it actually has a pluggable backend. So this is using, I think it's Coin. I'm actually not sure which backend we're using, but we're using the free open source one. I think actually our team, before I joined the company, did experiment with Gurobi, which is sort of the fancy, expensive one, and it was able to speed it up by some amount, but it wasn't worth it to us. Yeah, so I mean, generally, you have one run cut for weekdays, one run cut for Saturday, and one run cut for Sunday. Your service isn't changing throughout, like they call it a bid period or like a 3-month period, so they don't have to be constantly rerunning this until they actually change their service. Is there a question from over there? Sweet. Rostering. So as we said before, run cutting is the problem of packaging trips together into runs for drivers. And then rostering is once you've figured out your runs, you want to package runs together into daily work weeks. we call each daily work week a roster. So this might be sort of the full, in our typical service that we run every week. Let's say this is a very small transit agency, and we found that we can sort of find 4 weekday runs that will cover all our trips during the weekdays, and then 2 runs on each of Saturday and Sunday that'll cover those trips. So each run starts at some time in the morning, finishes sometime at night, and has some like total number of hours that the driver is working. So in addition to like labor rules that we have that sort of limit what people can do per day, there's also labor rules that limit what can happen within a week. So often there'll be rules that will say a driver can't like finish work at midnight and then be forced to come in at 6 a.m., which seems pretty humane. They might say that if they work more than 40 hours in a week, there's some overtime that they get for every hour in addition to 40. Or they might, let's say, have a weekly guarantee where they get 40 hours like guaranteed. So if they only work 32 hours, they're still paid for that full 40 hours. And so this is basically a potential roster, which would be assigned to one driver. Then you might create another roster. So this spans both weekdays and Saturday. And then this is basically an example of a full rostering over your weekdays. So basically every run is covered, and the colors sort of correspond to people that get that work those same set of runs. Does that make sense? Normally what they'll do, once they have this, once they've sort of like figured out an optimal rostering, is they'll post something like this to all their bus drivers, and the bus drivers will bid on different rosters, basically just like choose the ones that they want in order of seniority. So again, we have a constrained optimization problem, and it looks pretty similar. So we've got this objective, which is to minimize the summed cost of all rosters. Right? Each roster is going to have a cost, which is basically how much it costs to pay these people to work all this time. We have constraints, which is that each day run has exactly one roster. So you're not going to assign 2 people to cover run 2 on Tuesday, and you're not going to assign 0 people to cover run 2 on Tuesday, because then no one would be operating your service. And then again, you have labor rules. Like for example, the rule I talked about, where you have to have a minimum number of hours between getting off work one night and starting work the next day. Again, so interestingly, this is actually a weighted set partitioning problem as well. The sort of superset is the big set of all the possible day runs, and then each subset, aka roster, has a particular weight, which is how much you'd have to pay to operate to pay the driver. And then you want to partition the big set into subsets to minimize that total cost. As we know from last time, this is also NPHard. So what was really interesting about this is we tried to model this problem in basically the same way as we had modeled the Runcutting problem. We tried to generate a ton of rosters and then use those rosters to formulate this integer program that basically looked similar to this. And it just worked terribly. It would just churn and churn and churn. Even for like tiny agencies, it would take like hours to come up with a reasonable solution. So with that sort of the case, we thought about what are the other tricks in the combinatorial optimization toolbox. And again, this is sort of the area where having Python is really nice, and I'll talk about that a little bit at the end. But if you were building all of this out in C, you could spend a lot of time and create this really hyper-optimized thing that would work really well for some technique. But often it's very unclear what the right technique is going to be until you try it. And trying a different technique will often sort of lend you maybe 10 times the more the performance that like micro-optimizing the tight bits of code would allow you. So the technique that we ended up trying out was called local search, or other people often call this hill climbing, though in our case it's really more like hill descending, because we're trying to minimize a function. Raise your hand if you've heard of this before. Awesome. So just as a brief refresher for those who have not, the idea is, as before, you have this big space of possible solutions, and you can think of each point in that space as a possible allocation of runs to rosters. For local search, you define some sort of neighborhood. And the idea of a neighborhood is it's a set of solutions that aren't exactly the same as that solution, but they're close by some sort of like definition of close that you have. So then at each point, you can, you basically start with some solution, and it's not necessarily the best one. It might not even be a feasible one. But you explore the neighborhood of points or the other solutions that are nearby that solution. Maybe you enumerate all the different places that you could make a move to. You pick the best one, and then you sort of like make that move. Rinse and repeat until you hit some sort of local minima, and there's no way to find a better solution from there. So integer programming, on the NPHard sort of like how do you solve this problem trade-off curve, it sacrifices this notion of like it might you're going to get the best solution, but it might take forever. With local search, you're saying you might not get the best solution, but it is probably going to finish in some reasonable amount of time. The trick to defining a local search algorithm is basically finding a neighborhood that you think is reasonable. In our case, we define the neighborhood by swaps. So a neighborhood, is equivalent to some operation that you can do to mutate an existing solution and get some solution that's very similar to it. This is what a swap might look like. So each row is a excuse me. This is, let's say in a very sort of simple case, we only have a rostering that needs like 2 drivers. Each row is the set of runs that one driver is going to do. So driver 1 is going to drive a 8-hour run on Monday, a 9-hour run on Tuesday, a 9-hour run on Wednesday, so on and so forth. Driver 2 is going to drive a 7-hour run on Monday, 8-hour run on Tuesday, so on and so forth. And let's say that in our particular case, we have some sort of overtime rule after 40. So 9 times 4 plus 8 is 44. And so that would lead to basically 4 hours of overtime being required by the agency. So a swap would basically say, let's look at driver 1 and driver 2 and just pick some day of the week and swap whatever they've got on those days. So we could take this 7-hour run that driver 2 is driving, give it to driver 1, and take the 9-hour run that driver 1 is driving, give it to driver 2. And so driver 1 now only has 42 hours total for the week, so that's only 2 hours of overtime, and driver 2 is still underneath that 40-hour limit and doesn't get any overtime. So this is like a pure win for the agency. They pay less. The drivers don't have to work as unreasonable hours. Things are a little fairer. So this is an example of a positive swap that we might want to do. For local search, we're basically just sort of trying this over and over again. So we'll take 2 pairs of drivers, aka 2 pairs of rosters, and see is there anywhere in the week where we can swap things and increase our efficiency. Swapping doesn't necessarily mean leaving both of them with a run. So if we picked Saturday for a swap, that would basically just mean moving that run over to driver 2, and driver 1 would not have a run. Any questions on what this swap operation looks like? Cool. It's also notable that you could have a. Oh, sorry. Go ahead. We did not. That would have been pretty cool. But right. So yeah, I'll talk about that in a second. It's how we tried to deal with that. But yeah, we haven't ultimately compared. Well, yeah, I'll talk about that in a second. So this is basically what the algorithm looks like. We'll sort of enumerate the set of all possible moves. We keep trying to make a move until we can't make a move. And this is just sort of counting the number of moves. So as you pointed out, the problem with like hill climbing algorithms, it's very easy to end up in local optima. So you might find some sort of situation where there's no way to improve on that solution, but you definitely don't know whether that is better than the global set of all solutions. The way we tried to get around this was with a stochastic approach, and basically that meant that instead of choosing the most efficient every move every time, we would just pick some move that seemed that seemed all right. What this means is that every time we rerun the algorithm, you end up in some other place in the search space. And basically, what you can do is just run it multiple like tons of times with different random seeds, and see if you're able to get anything better. So the idea is sort of if you keep rerunning it, and after a bunch of different times you're not able to get a solution that's better than X, you can be like decently confident that that you're like getting close to the best you could get. So this isn't this is a heuristic. Again, it's not 100% scientific. If we want to be a little bit more rigorous, we could have tried throwing the problem into a integer program and sort of like waiting all those hours and see how our best local search solution comes up with, or like compares with the best integer program solution. But in generally, what we found is that this has been satisfactory. So it's pretty crazy. Basically, like we tried out this approach, and it immediately started like completing within tens of seconds and giving better results than all the other approaches that we had tried before. So that leaves this sort of question of, we have these two weighted set partitioning problems. At the surface, they're basically the same things that are going on. Why does integer programming work so much better for Runcutting, whereas local search works so much better for rostering? And this is a hunch I have that we haven't sort of like academically proved, but my sort of understanding is that Runcutting is this much more jagged search space. So there's lots more constraints, right? There's this sort of like geographic notion of you can't drive this trip after you drive this other trip. It's easier for trips to overlap. Like when you're rostering, you assign one run per day, and there's no notion of like you can't swap these rosters because they overlap in time in this weird way. And so generally, the Runcutting search space is just a lot more jagged. There's a lot more stuff that's off limits. It's hard to come up with a neighborhood where you're going to be able to make any swaps at all or make any movement. The rostering problem, on the other hand, it's very likely that there is some sort of close-by solution to a solution. And I think of the problem as more like this sort of smooth basin. The space of possible solutions is much larger. So if you try to like enumerate all of those, or like all the rosters, and throw them into the problem, it's just going to be like way more than the number of runs. But if you sort of just like hill climb down it, you get decent solutions. So last of all, I touched on this before. We use Python for both of these. I, in the past, have like tried to code up these algorithms in C or Java, and I think the reason that Python at least has been the right choice for us so far is that often the speed that you can try out an algorithm is more important than the particular like speed of any particular algorithm. The like more broad algorithmic choices that you make tend to have a like much more impact on final performance than like minor, let's say like CPU cache line optimizations. We're at the point where we're trying to speed up our Runcutting algorithm now, and we'll probably use Python or some sort of callouts for the most performance critical pieces of the code. But as a sort of like settling on the best solution, Python has really been a choice that's worked out well for us. So I think that is all I have. Are there any more questions that I can answer? Sure. Mm-hmm. I see. We did not, but there is a bunch of, yeah, so first of all, it's a great point. Second of all, there's a bunch of literature on this stuff. On the scheduling stuff, yeah. If you want to like read about any of it, they normally call it the crew scheduling problem, because you see it in like airlines and rail, and they've done that mathematic groundwork. Again, yeah, the integer. I don't want to oversell what we've done here. Like this broad integer programming approach isn't something that like we invented, but we picked it out of a set of papers that and thought it looked promising. I thought about it a little bit. I think it gets very hairy because a lot of the sort of tough stuff is in all the specific labor rules that you have. So like when you look at actually like expressing this to PuLP, it's more lines of code than this, but it's not that many more lines of code than this. And so I think a lot of it would be very specific to our the particular like bus scheduling problems that we solve. That said, I think there are some sort of like workforce scheduling packages that are out there. So integer programming, like what's happening behind the scenes, is it basically is enumerating the entire solution space. It has these clever tricks where basically it can prune branches of the solution space. So if you think of the solution space as a tree, or basically you can say like does it include this run, or does it not include this run, and you branch there. Often when you're exploring a tree, you can sort of come to the conclusion like, oh, it's already so expensive down this path that nothing we try out in this is provably going to produce something better than what we've already found. But yeah, it really is sort of enumerating the whole solution space. So when you say caching the solutions, you mean caching the full solution to the final problem, or caching like sub? Yeah, I mean, so when it comes to sort of the overall problem, we have talked about caching solutions. I mean, in general, the details will change in minor ways enough that you can't like necessarily cache the whole thing. So let's say in our rostering problem, you would never. Well, I don't know if that's even true. We could cache. Yeah. So when it comes to that stochastic local search, where you're sort of like trying random things, it is very possible that you would sort of run into the same solution you had before, and you could save time by not exploring. We haven't done that yet. That's worth trying. Interesting. I have not. I can't think of a good way to do that, but there probably are good ways. So it's not. It's not super. It wouldn't be super applicable to our use case because we generally know that like if we have a run-cutting problem, integer programming is going to be better, and if we have a rostering problem, local search is going to be better. I'm sure that there are people smarter than me that have thought about this before a little bit. Yeah, we actually did try it. I mean, so the particular, we did try it out. Yeah, I mean, so what happens with the hill climbing is generally you quickly get to a point where it's impossible to make any any improving move, and the integer programming sort of does a better job of then like considering a whole other part of the solution space that might be better. Yeah, so I mean, hill climbing in machine learning ends up looking pretty different than hill climbing in discrete optimization. So in, in machine learning, like often you're using a gradient to sort of tell you where to go, and it's all about figuring, like it's a continuous space, and your the solutions are like, you know, could have arbitrary decimals, and a lot of the like trickiness is in finding a good step size. In the discrete world, you don't really have this like notion of a step size as much because you're just like discretely jumping to a nearby solution. Also, it was fairly quick to implement. There's not a name for that I know. I mean, it seems like it would be very fun to work on, and I could imagine that our customers might find that useful. I don't off the top of my head have an idea about the best way to approach that. Sweet. Oh, one more. Often bus drivers often the senior bus drivers will actually pick the most hours. So okay, so the way it normally works is they pick rosters in order of seniority, and often the senior bus drivers will pick the roster with the most hours. They just want to get the most overtime. Right. So in America, it's like that. In Europe, it's much more about fairness, and they actually will swap rosters like every week. But here it's more like if you're a new bus driver, you get the worst thing, and if you're yeah, it's actually pretty wild. Often the unions will really want you to create like a couple good runs for their drivers that have been there for a long time, even if that might mean messing up the runs more for the other ones. Yeah, I mean, I don't think they're optimizing for disparity in the sense that they want things to be bad for the other drivers, but their sort of paramount importance will be having really good runs for the most senior drivers because they've normally been in the union the longest and sort of have the most leverage. Right. So they're not expressed or negotiated in the labor contracts. This is by far the hardest problem that we are trying to solve as a software company, is like making it intuitive for trans agencies to express those kind of preferences that they have. Right now, it just gets, you might say there's a penalty for every hour of, so sort of the number one things that drivers don't like is being at work when they're not getting paid, which makes sense. I wouldn't like that either. And so what they hate is these split shifts where they'll have to come in for like 4 hours in the morning, then have like a 6-hour, sort of like dead time in the middle, and then have to work 4 hours later. So we might have a penalty that says, for every hour of dead time, consider that like another worked hour. And so it'll try to avoid those. And so that's a parameter that right now we have in our software, but we found that it's pretty tough for them to sort of conceptualize how that would end up working for them. Cool. All right. Well, thanks everyone for coming, and I'm happy to answer more questions, in particular afterwards.